Hello, class. Welcome back. This is lecture 2. Today we are talking about linear functions, and I've got a hairband on so that my hair will not cover my eyes anymore as I speak. All right, hope that helps. Okay, so linear functions. So let's just jump right in. What is such a thing? A linear function. So remember last time we learned about what functions were. We always write them as f of x equals blah, blah, blah. So a linear function is a function, of course, it's in the name, but it's a special type of function. So we still write it as f of x equals, and then over here, there will be stuff with x in it, but it's sort of a mystery right now. Sort of like leave it blank. We'll see what it is later, but the property that a linear function has, what makes it be a linear function as opposed to just any old function, is that it has constant rate of change, or you could say that it's change in y values divided by its change in x values. So if I divide, and I'll say what these are more in detail later, if I divide this change, then this will always be the same number. Okay, it's constant. It does not vary. So right away, we'll just jump into an example of a linear function and see how it has this property. It's a bit abstract right now. So here's an example. 3x plus 1. This is a linear function example. And it's a linear function because it has this property. So let's see that it has this property. So it's a linear function because the idea behind this property is that if I take any two x values, really can be any two x values, and because we're taking two x values, we don't just name them both x because that could get confusing. They can't both be x really at the same time. What we do is we give them little subscripts. So we'll call the first one x subscript 1 because it's the first one. So say like it's 5, and then the other x. So we take any two x values we want. It doesn't have to be 5 and -3 like I'm picking. It could be any two. But I'm calling them x1 and x2 because they are my first choice and my second choice. So if I take any two x values, then find the corresponding y values, which remember the corresponding y values are just what you get when you plug in these numbers to the function. So if I plug in x1, that means I'm really plugging in 5. And plugging in 5 really means look at this function and change all the x's to 5s. So 3 times, this becomes a 5 plus 1, gets me 15 plus 1, gets me 16. So the corresponding y value for x1 is, I'll call y1 because there's going to be two y values, and this one is in it 16. So remember, this also means, just as a slight aside, that 5, 16 is on the graph. This will come in handy later, but for now, just a little aside. So find the corresponding y values. So that's one of them. The other one would be coming from plugging in the other x value, which I said I'm going to use -3. And I'll do the same thing. So I'm just changing this x, that used to be an x, into whatever number is here. That's how functions work. So just dropping it right in there and then use calculating. So 3 times -3 is -9 plus 1 is -8. So my second x value corresponds to a y value of -8. So I have these 4 things, these 2 x values and these 2 y values. And the idea behind this linear property is that the change in y divided by the change in x will always be the same. So what is change in y? What does that really mean? Well, the change is between 2 places is just how far you've gone, or the distance or the difference. So it's really just a subtraction of the 2 things. So the change in y from y1 to y2, that just means y2 minus y1. So the change in y is just -8, because that's y2, minus 16, because that's y1. So that's the change in y, which I guess would be -24. So that's how much the y values are changing from one to the next, aka how far away it is from -8 to 16. And the change in x, very similar idea, is you can think of it as, again, from x1 to x2 is just how far away it is. And you could just calculate that by subtraction. So it's x2 minus x1. So in this case, it would be 5. Wait, why did I write 5? Both. Whoopsie, one of these was a -3. Little typo. I will do this sometimes. Sorry about that. x2 is not supposed to randomly change. It's -3. And that is what I plugged in as I was supposed to. Very good. Good job by me. But suddenly over here, I changed it into a 5. My apologies. It never changed. Voila, magic. Okay. Back on track. So -3 minus 5, because x2 is -3, and I subtract, and x1 is 5. So you do have to be careful when you have too many negatives going on, but it's always just the first number, sorry, the second number minus the first number, second number minus the first number, and just be very careful. Okay, so -3 minus 5 is -8. So then what this linear function property says is that no matter what 2 numbers I started with, so in this case I started with 5 and -3, but no matter what, if I pick something else, no matter what, I'm going to get the same answer here when I do change in y over change in x. Whatever number I get will always be the same. So here, this is -24, this is 8. -24 over -8 is, negatives cancel, 24 divided by 8 is 3. 3 goes into 24 8 times. Okay, so this will be the same no matter what x's you start with. So I chose -3 and 5. So if you do it all over again, you'll get the same answer. Pick whatever 2 you want. Obviously, I don't want to do giant numbers like this. It'll take too long. But if you do the whole process, same exact process, you'll get 8. You'll get, sorry, not 8. You'll get 3 again. That's the property of linear functions, that this will always work. So let's see. Let me actually, let me do another, but in a much quicker way. So I will do smaller numbers. X1 is 0, X2 is 2. So then my Y1 that I get and my Y2 I can figure out by just plugging in 0 or plugging in 2 to the same, still using the same function. I get 3 times 0 plus 1. Over here I get 3 times 2 plus 1. 3 times 0 is 0 plus 1 is 1. 3 times 2 is 6 plus 1 is 7. So this is my Y2, my Y1. So now if I do Y2 minus Y1, that's my change in Y. I divide that by X2 minus X1, that's my change in X. Then what I'm doing is I'm doing is this Y2 minus Y1, 7 minus 1 over X2 minus X1, 2 minus 0. I better get 3 again, and I will, because on the top I'll get 6, and on the bottom I'll get 2. 6 divided by 2 is in fact 3. So it works, and it will work no matter what two numbers you start with. That's the property that linear functions have. It's always good to see a non-example, something that's not something that you just learned about. So just for comparison, so meanwhile, x squared, this function is not linear because it does not have this property. So if I pick x1 equals, say, 3 and x2 equals 4, then I do y2 minus y1 over x2 minus x1, it's going to be a little bit different. So x2 minus x1 is going to be 4 minus 3 on the bottom, but on the top, what's y2? That's going to be plugging in 4 to the function. So what is the function now? It's squaring. So you change that x into a 4, and you calculate it, and you get 4 squared is 16. So that's up here. And if you do, you're going to get y1. That means you plug in 3 to the same function. 3 squared is 9. So what do we got here? 16 minus 9, is that 7? 4 minus 3 is 1. So here we get 7. But if I pick two different numbers, if I do like 0 and 1, just to make it easier, so you can check it very quickly, but y2 and y1 you can calculate very quickly. Y2 will be 1 squared is 1, and y1 will be 0 squared is 0. So now if I do y2 minus y1 over x2 minus x1, I do not get the same number. I do not get 7 always, like I would for a linear function. Whatever I got the first time is what I would always get. Now I can get something different, and I will. So y2 minus y1 over x2 minus x1 is just that. 1 over 1 is 1. So not the same. Okay, so linear functions are special in this way. They will always get you the same rate of change, is what it's called. This will always be the same. Okay, and because it's always the same, we give it a special name for linear functions. Okay, so the value, sorry, so now just only for linear functions. So for linear functions, the value that we've been calculating, y2 minus y1 over x2 minus x1, or you could always write it as, because y2 comes from plugging in x2 to the function, you could write it like this. And because y1 comes from plugging in x1 to the function, you could write y1 like that. It's the same thing. These are both the same. This value, whatever it is the rate of change from x1 to x2 is what it's called. And for linear functions, It's called the slope. It's always the same. And it's called the slope. And we usually name it M, typically, because it's just some number that we call M once we know it. And that's the idea. Okay, so in general, it's called the rate of change, but for linear functions, it's called the slope. Linear functions are very special and always is the same. So we can just name it a single number called M, the slope. Okay, so let's do a little example here of finding the slope. So find the slope of the linear function. So a linear function is something that has a slope. So we can do this, find the slope of the linear function, but we're not going to be given the linear function. Instead, we're just going to be given that it's passing through 2 points. So different than the previous example, passing through the points 2, 6, and 3, 10. So in the previous example, we're given f of x equals blah de blah way up here. Let's just quickly look at it, this guy. And we found the slope by choosing our own x values and then doing this y2 minus y1 over x2 minus x2, x2 minus x1, using the things that we picked. But we also had the function to work with. This time we don't, but we don't need it because we already have the y values corresponding to the x values, and that's the key. So we don't even need the function. So we don't need to know f of x. In fact, later we're going to figure it out. What we know is that y2 minus y1 over x2 minus x1 equals this number m that we're looking for. No matter which two x values you start with, but these x and y values, they are related to each other. Really, the x value, x1, you plug it in and you get the y value, y1. That means x1 y1 is a point on the graph of the function. So really, you can say it like this: no matter which two points on the graph, they got to be on the graph. They can't just be like whatever numbers you want. They got to be on the graph you use. So we just so happen to be given 2 points on the graph. So all we have to do is sort of name things. So I'm going to call this one on the left x1 and y1, and I'm going to call this one on the right x2 and y2. So then this little formula tells us the slope. Very quickly. So y2, that's 10. y1 is 6. And x2 goes with y2, so you got to keep it the same. So x2 is this 3 over here. And x1 goes with y1, so it's this 2 over here. Lots of lines. And then I can just do it very quickly. 10 minus 6 is 4, 3 minus 2 is 1, 4 over 1 is 4. So that's the slope. And I don't have to check anything else because it's already told to me that it's a linear function. So all I ever need is for this to happen once, and it'll always be the same. So it'll always be 4 no matter which 2 points I use. Doesn't matter that I use these ones or different ones. So this leads us to just giving away the secret, which is linear functions always have to look a certain way. They always look like this. M is your slope times x, so just write it as mx, plus some mystery number here, which we'll get to in a second. So m is the slope that we've been talking about. And b is, well, you could think about it as what you get when you plug in 0. Because if I plug in 0 for x, then I get 0 times m plus b is just b. And it's also called the y-intercept, the y value of the y-intercept, which is just where the graph hits the vertical axis. So it'll look something like this. 0, comma b is where the linear function touches the vertical axis. Okay, but we'll figure out how to get b very easily, so don't worry so much about this yet. Okay. The point is that knowing 2 points, like we just saw in the previous example, is enough to determine a linear function. So I can say exactly what f of x is if I just have 2 points. I can say what this is exactly. We can figure out m, as we just saw. We did just figure out m with exactly 2 points, but now we're going to see how to figure out b. Okay, so let's jump right in. Determine the linear function. So it's got to look like this automatically. I'm just figuring out m and b, which passes through the 2 points, 2, 6. So these are the same points as before, just so I can save myself some work. And so the steps are, well, I already know the slope m, but normally that would be the first step. Get the slope, which we already did earlier, and it turned out to be 4. So you can rewind to see that again if you like. Copy paste it right there. Second step is get b. And we're going to streamline this process after the first time we do it, but this first time will be kind of long. So because we're going to sort of reason through why it's working. So it's a bit tricky. So the idea is that since m always equals this, whoops, y2 minus y1, x2 minus x1, no matter what, for the keyword here is any 2 points, what we're going to do is we're going to be a little bit sneaky. We change one of the points into, instead of calling it y2, sorry, instead of calling it something, we're just going to call it xy. And the one we're changing is x2 comma y2. But we stick it back in this formula here. And then this creates an equation. So we create an equation. So x1 and y1, those will just be regular old numbers from a point that you're given. X and y will be back to being variables again, but they are variables that represent points that are on the line because they're fulfilling this equation. So that's what we're going to do. Okay, to create an equation called point slope form. That's what people call this thing. So let's do it. So I'm just going to change my x2 into x and my y2 into y. And then what I'm going to do is plug in one of the points that I know. So I don't have to pick the same one that I called x1, y1 before, which was 2, 6. I could actually rename it at this point, but just to keep things straightforward, let's not do that. So this one previously was what we called x1, y1. So we'll keep it like that. So 2, 6. So y1 is 6 and x1 is 2. So I'm just putting those numbers in here. And then we got a little bit of algebra on our hands. Then we're just going to solve this equation for y. But notice I didn't use one more piece of information. We also know already from before, in this situation, m equals 4. So we're also going to put that in. And then we're going to solve for y, and then this will do it for us. So this is a bit of a tricky algebra situation if you're not used to it. But on the right side, you have division. So if I want to get my y alone, what I need to do is I need to multiply both sides by x minus 2 so that, and then people like to write the number in the front, so we'll do that too over there. So that on the right side, the x minus 2's cancel. And now I can get y alone. But people like to write y on the left always. So we're going to also do that. We're going to switch it up. That's okay. You can switch on equal sign. You can just switch sides as long as you keep everything exactly the same very carefully. And then to solve for y, I'm going to add the 6 over. But first I'm going to distribute this 4 because people like to do that. And then when I add the 6 over to both sides, I can now combine my -8 and my 6 to get -2. And this tells us the final answer. The function we were looking for is 4x minus 2. So our b was actually -2. If you want to go back and put it in terms of m and b and saying what they are. But all we're doing at the very end here is rewriting y as f of x. Okay, so in practice, we don't do all this work every single time. We can streamline this process. Don't have to reinvent the wheel every time. In practice, we just jump to this using this little formula here. It's called point slope form. And it's after you already have multiplied the x minus x1 over and rewritten it a couple times. So we just use this. We plug in m, which we know, and the x1, y1, which we're given. Okay, so let's do an example, a streamlined example. Determine the linear function passing through -2, 3 and 4, 5. So first step, this time I don't know the slope yet. So I'm going to do that first. M equals, as long as I just am safe and label everything nicely, x1, y1, x2, y2, then I can use this formula very quickly. So y2 minus y1 over x2 minus x1 becomes y2 is 5, y1 is 3. It's easy to get mixed up. X2 is 4 and x1 one here, got to be careful, is -2. We can't just pretend we already included the negative. We have to do 4 minus -2. That minus is already built in. Can't forget about it, just because there's another one on the 2. Okay, so we're just copy pasting nicely, not messing up. And now is when we can mess up, when we actually do some calculations. So 5 minus 3 is 2. 4 minus -2 becomes 4 plus 2. So that becomes 2 over 6, is, you can write that as 1/3. So that's my slope. Now I can use my new little formula that we just figured out. So y minus y1 equals m times x minus x1 becomes, sorry, becomes, so I got my m, x and y, they don't change, but what changes is x1 and y1 with the point that I use. You could use either one, but I'm going to use the one that I already called x1, y1, just to be consistent. Give me 1 second. I need a cough. Okay, I'm back. All right. So as I was saying, I'm just going to put in 3 for y1, because that's what y1 is there. And I'm going to plug in -2 for x1. So you got to have these parentheses just to be extra clear on your algebra, not to mess up. Otherwise, you're going to forget a negative and think it's already there. Something like that will happen. Okay, so then after you've copy pasted like that, you just have to simplify a bit. So this becomes 1/3 x plus 2. You can now distribute the 1/3 to get you 1/3 x plus 2/3. Then you can add this 3 over to solve for y. And unfortunately, we got some fractions here to deal with, but that's okay. I need to get a common denominator between these two fractions here. So I'm going to multiply this one by 3/3 so that it has a 3 on the bottom. And that way I can add it to this. So 2/3 plus 9/3 gets me 11/3. And so just to be completely done, f of x is what we're looking for. The linear function, we change it back. We don't want to write an equation, even though it's the same thing. We want to write using our fancy function notation. But that being said, sometimes we do keep it the other way, and we'll see that right now. Okay, so sometimes we say, instead of linear function, we say something like, you've probably heard this before, the line instead of linear function. So you might hear like, find the line that passes through blank. And then you write an equation, y equals mx plus b, called slope-intercept form. But this is actually what we've been doing the whole time, secretly. All you got to do is not do the last step that we just did, and you've done that. So we already actually have done this. We just didn't call it a line because we're trying to deal with functions. And the reason people might keep it like this instead of changing it to functions is because they sometimes like to manipulate this equation and write it in standard form. I'm not going to really do this, so I wouldn't worry too much about it. But what they do is they move the x's to one side with the y's and leave the number on the other side hanging out. So we could do that here. All we do is multiply everything by 3 to both sides to clear the denominators very nicely. And so 3 times 1/3 is 1, so you get 1x left, plus 3 times 11/3 is 11, the 3's cancel. And then standard form would be to subtract the x to the left. So you leave the number alone on the right. Some people do this for various reasons. Sometimes it's more useful to write it this way. But, and we probably will do that in a long time. But for right now, we won't be doing that much. Okay. The point is that that's all the same as what we've been doing, is finding the line instead of finding the linear function is the same thing. So let's do an example like that. Find the equation of the line. So it's a little bit different because they're going to tell you the slope instead of 2 points. They're just going to tell you 1 point. But actually, it makes everything easier because I don't have to even find the slope. They're just telling it to me. So what's different is that now I'm finding the equation of a line instead of finding the linear function. And now I have a slope and a point instead of 2 points. But it works the same. Step one, we need the slope. Well, we got it. We don't have to calculate it this time. It's told to us it's just 3. We still use this y minus y1 equals m times x minus x1 formula. But now we only have 1 point to choose from, so that's going to be our x1, y1. So y1 will be 4 and x1 will be 1. And I will then plug these in. So m is 3. And do what I did before. Distribute this 3. Add the 4. And then I will get y equals 3x plus 1. And instead of saying it's a linear function, I'm saying it's a line. So I'm leaving it as an equation instead. And so I don't change it to function notation. And that's the only difference between this problem and the previous problem, is we just don't change it back to function notation. But everything else works the same. Okay. So the main reason that linear functions are called linear functions and is that they are the same as lines in terms of these equations are the same, but also when you graph them, they create straight lines. So the name linear function is because the graphs of them create straight lines. And we're going to learn how to graph them next time. So don't worry about it now, but this is why the name is what it is. The last thing we want to do is just sort of mention different types of lines or linear functions. So it's good to sort of categorize things. So, and this will come back when we graph, but it's good to mention now. So various things can happen, you may have seen so far. So our slope m can be positive, negative, and it can also be 0, which we have not seen yet. So something like this, 5x plus 2, that's a positive m. M equals 5 is a positive number. Or 16x minus 12, something like that. M is 16, still a positive number. It could also be negative. So you could have something like negative 7x plus 4. And what this does is we can think about it before we even graph, but what it's saying is the rate of change is positive or negative. So up here, what's happening is as x goes over, y is going to go up. So we'll see that visually next time. Here, as x goes over, whoops, the rate of change is negative, so y is going to go down. The graph will go down as you go over instead of up. But in fact, m could also be 0. So then it looks a bit weird. 0 times x plus b. 0 times x is just 0, so you would just write this as f of x equals b. So you can have things like f of x equals 10, or f of x equals 2. And these are also linear functions, even though they have no m. Well, they do have an m. It's just hidden away because it's 0. And they're very weird to think about because normally when you use a function, you like plug stuff into it, right? So like what happens if you have a function like this? What happens if you plug something into it? What's f of 2? Well, this function is weird. It has no x's on the right to change into 2's. Instead, you don't change anything. It just stays as 10. The whole point of this function is always 10. No matter what you plug in, you're always going to get 10. Because there's no x's to do anything. You put a smiley face in there, you still get 10. No matter what you do, you get 10. So this is what happens when there is when the slope is 0. And we'll see pictures of that next time too. Okay, so that's it for this time. I will see you next time. I hope this video was shorter than the previous one. I think it was.